All right, final exam cheat sheet, picking up here with problem number 4 from our final exam. This problem is going to come from Chapter 4, Section 5, dealing with the use of the quadratic formula to solve these sorts of equations for x. And as you can see in this equation, as with all equations, I should be able to solve for a variable in there. But I run into a problem with this format because the x squareds and the x cannot combine. And if I were to isolate either one of them on one side of the equation, the other one would have to be on the other side. And so I fundamentally can't solve for x using the traditional inverse operations. In this case, we're going to be applying the use of the quadratic formula. Now, there are a few other techniques throughout Chapter 4 as to how to solve these quadratics for x. The quadratic formula is pretty much the foolproof way of which to do it. And just to quickly give you a background as to why this would be necessary, what we would use our results here for. So fundamentally, we're going to be able to solve for x. And the fact that we have a quadratic, or this exponent of 2 here, means that there are actually technically going to be up to 2 different possible results here for x to satisfy this equation. And what we're ultimately finding when we get these potential 2 results for x, these will represent what we call x-intercepts, or zeros in the coordinate grid for this U-shaped quadratic parabola. Okay, so again, if you can imagine a U-shape, the maximum number of times it can cross the x-axis, it can cross up to twice. It could also only touch it once if the vertex is the only thing touching the x-axis, or it could completely miss it altogether. Those are all possibilities and part of what makes the quadratics a little frustrating for algebra students and stuff. But the potential, what we will be able to nail this down to 2 possible x values. They'll represent x-intercepts for where that U shape crosses the x-axis. That's why it's actually set equal to 0 here, because if you were to imagine this as a function, it would be equal to y. And so by the fact that y is replaced with the 0 right here, it's when y equals 0, which is another way of saying it's when it crosses the x-axis, the horizontal axis. All right, well, fundamentally, we're going to need the quadratic equation, so let me just write that out for us. Again, if you do not like memorizing formulas, write these things down so that you do not have to memorize them. So this is by far one of the most infamous of formulas in all of algebra, because it involves so many different math operations in it. This is the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. So where do these a, b's, and c's come into play? They are the coefficients to each of the respective positions in the standard form. So just to remind us, we've gone through this in a few different problems, but a is going to be whatever coefficient is attached to the x squared, the positive 5 here. B is whatever is attached to the x, in this case, the negative 12. And yes, that sign does stay attached to it. C is going to be this other value over here that has no x attached to it whatsoever. It'll be a positive 4 in this case. And essentially what we're doing here in this formula is we're just simply applying each of these coefficients into this equation and solving for x. There is an origin story as to where this formula comes from, but you can revisit Chapter 4, Section 5 notes, and particularly the recording for that section where you can see the proof of that. But let me move on here. So I usually take a couple of steps because there's so many operations happening in here. I usually take a couple of steps just to work through it so I can manage it. So I usually take a step just to substitute in the correct values. Now this negative sign here, anytime I have a negative sign, I always take the time to write it again. And if I happen to have a negative value that comes next, I'll just write the negative sign twice, like we're going to see here. So I'd start with negative b. Now b is this negative 12, so I'll write a negative 12. Yes, that sign will change. Many of you would do that in a single step, but I like to take the time to draw it twice just so I can know I need to make that step. I have my long square root now, so then I have that b squared. That same negative 12 is going to be squared. And I wrote it in parentheses because this negative multiplied by itself will end up canceling when it's squared. So it'll become a positive 144, but we'll come across that in a minute. Minus 4 times a times c. A here is that positive 5 out front, and c is that positive 4 at the back. All of this mess is over 2 times that same a being the positive 5 out in front. So there's my substitution. At this point now I'm just doing the operations as they come. So again, I usually take a couple of steps for this, so bear with me. The negative 12 turns into positive 12. The plus or minus here represents the two potential values for this x, and we'll come across that solution in a minute. And then underneath the square root, again, I take time to do each of these. I'll do this b squared element first, so negative 12 times negative 12, or negative 12 squared, gives me a positive 144. You should definitely never get a negative answer right here in this piece, so double check that. And then I always write this minus sign, and then I just do the 4 times a and c as my next little chunk. So 4 times 5 is 20. That 20 times 4 is 80. And so I'll take an extra step to subtract the two. All of this is over 2 times 5, or 10. All right, taking another couple of steps to do this, just whittling it down as I go. Still positive 12 out in front here, plus or minus. Now I'll do what's underneath this. 144 minus 80 on a calculator will give me 64. This will end up being a nice friendly result. There is a nice whole number square to the 64. Still all over 10. It's nice and condensed now, so let's just keep going. The square root of 64 will, on your final exam, this will end up being a nice friendly whole number, so rest assured you'll end up with something like that. But we're going to end up with this result. 12 plus or minus the square root of 64 is 8 all over 10. All right, well, now at this point, technically I can split this up into two possible solutions at this point. All right, so I'm going to break this up into the two different possibilities. First off, dealing with that plus 12 plus 8 over 10. All right, and 12 plus 8, just to finish this problem out, is 20, and I'll end up with 20 over 10. This does end up reducing. 20 over 10 reduces to 2, so x here, my first value that I get for x is 2. If you wanted to check your work, you could plug that 2 back into the original quadratic at the beginning. It should make the equation work. So that left-hand side, that entire 5x squared minus 12x plus 4 mess, if I plugged in 2 for x, should end up equaling 0. Right, but I do have another possibility here. It's when I have 12 minus 8. So I do also have this equation, right? 12 minus 8 is 4. And I have 4 over 10 as my result. 4 over 10 also reduces. This will end up giving me 2/5. This is my other possible solution. So actually what this would visually represent on a coordinate grid, and the whole reason why this quadratic formula is valuable, is that these two solutions right here represent where on the horizontal x-axis, whatever this parabola may look like beyond these 2 points, these are the two locations on the x-axis that it crosses the x-axis. So 2/5 or about 0.4 to the right, positive 0.4 to the right of the origin. That'd be the first interception point, and then positive 2 units to the right would be the second. So the U shape would definitely pass through those 2 points, regardless of anything else that's happening. So that would be problem number 4 on your final exam. Essentially, this is just identify the A, B, and C coefficients, plug them in, and then just be careful to take as many steps as you need, like I've done here, to get to your final solutions. You should have 2 solutions on this number 4. Okay, let's pick up with problem number 5. Problem number 5 will conclude our first semester review problems. Problem number 5, just like these previous 4 problems, will be the only representative from its respective chapter, being chapter 5. Chapter 5 is where we introduced probability, or the likelihood of an event happening. This problem will be a representative from chapter 5, section 5. Again, chapter 5 dealt with probability, and section 5 specifically dealt with what we call permutation versus combination. Essentially, you're going to be given a scenario that you need to count the number of possible ways that something can shake out. And this problem's a little unique because there are going to be different versions of the final that float out there. And this will really depend, this problem, the scenario that you're going to be dealing with, is going to depend on what you end up seeing on your exam. So let me just give really quickly what will be the case for everyone. And then I'll show you the 2 possible situations you're going to end up with. So first off, you're going to be told that there's a race happening. Right? And this will sound familiar from your first semester final, hopefully. But you'll be told there's a race happening, and I'll box this number for a reason. I'll come back to that in a second. But you're told you have 16 runners running a race, some event at a track meet. And the reason I boxed the number is because on your final exam, depending on which version you have, this number may be different. And that will come into play into how I calculate things. But you'll be told you have a race being run by so many runners. In this case, for this example, 16 racers. And then you're going to get one of the two scenarios that you're going to be asked to count the number of situations that can shake out. Situation number 1. Okay, so this is what some of you will receive on your final exam. You're going to say, find the number of ways All of your questions will start with that. And then you're going to get one of the two scenarios. Scenario 1, find the number of ways the racers finish first, second, third, fourth. There may be a different combination of this as well, but basically what's being asked here for scenario number 1 is you're basically looking for the order of the finishers. Okay, so again, if we're thinking of a race, if you think like a podium of finishers or medals being given out, first place medal is going to be different than third place, second than fourth, and those sorts of things. Okay, and there's a reason why this will be counted different than scenario number 2. Scenario number 2, we might say something like this. Count the number of ways that the top 4, we'll say, I box that number because again, this may be different on your final, that the top 4 qualify for CIF. CIF being like the playoff version of track and field for individual runners and racers. Okay, so there's a fundamental difference between these two scenarios. And if you look back at the title of Chapter 5, Section 5, again, the title is broken up into two pieces, permutation versus combination. Permutation, fundamentally, the order matters, like this scenario. In this scenario, the order matters because there's going to be a big difference between someone that's finishing first versus someone that's finishing second. You could have the same 4 people finishing, runner A, B, C, and D, and you could have them finish A, B, C, and D, but it's a completely different iteration when you have someone's finishing A, C, D, B. That's a completely different count than the original one. Whereas with the second scenario, where the top 4 qualify, that's the other version that's expressed in Section 5, where they talk about combinations, where the order doesn't matter. So in this scenario, if you had runners A, B, C, and D, it doesn't matter who finishes first, second, third, or fourth. The top 4 qualify. So whoever finished first gets the same qualification as someone that finishes fourth. So in that case, the order does not matter. And so whether you get a combination of A, B, C, D or D, C, B, A, that's considered the same combination of people qualifying. So that would be counted as a single instance. So let's just jump immediately how to solve this. And I'm spending a lot of time talking about where it comes from. The actual solution process is super fast. This is a permutation. If you get a question asking for the way that people are finishing in order, that is what we would call a permutation, and you'll be dealing with the NPR function on your calculator. I'll demonstrate that in a moment. For this one, this would be what we call the NCR function for combination. In both these cases, the P function and the C function are simply going to be buttons on your calculator. So you really just have to figure out what N and R are going to be in each cases. And in both these instances, they're the exact same. N will represent the number of total racers. And again, at the very beginning of this problem, I said that there was going to be 16 for this example. Your number may be different. Had there only been 10 racers, this number would be 10. If there were only 4 racers, the number would be 4. R is going to be the number of positions you're going to care about. So in this case, where it was first through fourth, R is 4. In this case, the top 4 qualifying, R is 4. Now, these numbers, again, are subject to change because maybe you only want to care about first and second finishing, in which case that would be 2. Or maybe the top 10 qualified, in which case that'd be 10. All right? So your scenario may be different on your final exam. But now let me just show off how to do this on a calculator. If you need help with these functions on your calculator, just feel free to ask even during your final. But you'll notice both the NPR and NCR buttons right here. Just to kind of walk through how this will be solved, I'll just do this one for the sake of the recording. You're going to hit the 16 first, the N value. In this case, for a permutation, I'm going to use this NPR button. It's now waiting for the R value, 4 here, 43,680 ways.